Hi there, I want to give another update on the time traveling debugger, aka the time machine. Since last week, so the top two tasks that I've been working on related to this project. Number one, the performance of this stringify function, which is the serialization function that I wrote in JavaScript to take an object and serialize it into a string before saving it to the database. And then the second thing, that was thing number one, and the second thing was to update the UI for the Zoom debugger. Since I just got something working, I got a jolt of happy energy, so that's why I decided to make this video right now. But I'm gonna report on what I did for thing number one first. So in order to optimize the performance, this is a wrong window. Okay, this is the right window. So in order to optimize the performance of the stringify function, which in the code it's $stringify. So all of my functions and global variables that I have outputted in the runtime, I prepended with a $sign, so that at user land, the programmer cannot make a variable name that conflicts with one of the runtime functions. Anyway, this stringify function takes an object that is, allocated to the program during runtime and converts it to a string. And then with the output of this function, the string will be saved into the database, going through this prepared statement. The problem was this stringify function was the top bottleneck in the execution of the program, and when this database logging is turned on. So I sort of set my sights on making this stringify function faster. And the way that I decided to do that, at least to try doing that, is to write this function in C++ as a Node.js add-on. I'm actually considering, I've never done that before, but I learned how to do it last week. The resulting code looks like this. The syntax highlighting looks really funky right now, but there's actually some good, please excuse the noise, native add-on, is this what it's called? So yeah, this is called C++ add-on. So the official Node.js website actually has a pretty good documentation about how to do this, and I found a couple of other resources other than this as well, but I'm gonna refer to this one. So for example, if you wanted to build a module that just has a function, you call it, you get a string back, then this is what you would write, right, in C++. You set it up, in the setup you have your C++ file, which mine is called stringify.cc, and then you need to set up this binding.zip file, and then off you go. One thing though, this way of writing an add-on, a so-called C++ add-on, is like no longer the recommended way. This way in particular, this way of writing it references objects or types that are defined in the V8 JavaScript engine, as well as other low-level libraries such as libuv, which is one of the backbones of Node.js. They no longer recommend you doing it this way unless you have some actual need to access V8 stuff or libuv stuff directly. So instead of writing it this way, they've the core team has designed something called the N API, which I think stands for Node API, and they recommend you write the C++ add-in using this API instead, which if you do it that way, you will not reference any V8 types or libuv types directly, and instead you'll be using all these wrapper functions, all of which prefix with the name and API. So that's what I did. And basically I rewrote this stringify function, which is about, I don't know, maybe 30 lines of JavaScript, and a little bit, let's say 40 lines of JavaScript. I rewrote this in C++. It ended up being a 185 line long C++ module. I will go through just a little bit of what is going on in this code, but I'm also considering making a separate video just about how to make Node.js C++ add-ons as well. If you are into that, please write me in the comments, and then I will take note of your comment. So first you initialize your module with the init function, which must have this signature, and then inside the initialization you can do a few different things, one of which is say I want the this one actually creates a function. I want the default export to be this stringify function rather than a property. So the way you actually use it is like this. Currently my code is actually not using this native module add-on, and I'll explain why later. But this is how you use it. You first require the bindings module, and then you ask for the stringify object within the bindings module, and then you get whatever your thing returns back. And in my case, it was this stringify function, which the actual definition is this guy. Again, I don't know why the syntax highlighting is a little weird right now, but whatever. This basically makes it so that the default export of the module is the stringify function. And then this is my stringify function. The entry point of every function that you write as a C++ add-on is always this environment variable, and then this callback info variable. With the callback info variable, what you get from that is you can get information about the arguments that were passed to the function. You don't get them as normal C++ parameters. You have to go through this info object and say, hey, can I get the callback info? In a particular, you want to get the argument count argc and the list of arguments from the callback info object. This setting the count to a certain number will give this function an expectation of how many arguments there are, and so it will only check up to that number. And then you set up this array, it'll populate this array with each argument that were passed in. And then so you send in this pointer to the argc and the pointer to the args. This is a pointer because in C an array variable is in reality a pointer, so even though that doesn't have that on it, it's still actually a pointer. I think the syntax highlighting looks weird because I did this define thing, but whatever. Okay. And then I have a little check to make sure you're passing in the right stuff. And then I have this stringify value function, which I wrote here, which checks what type of the value is, whether it's a string, a number, a boolean, a null or undefined, an object, or what. And if it's an object, it could be an array. Maybe little known fact, but an array in JavaScript is actually an object. So when it says it's an object, I then have to check whether it's an array or not. And in order to access these things, I have to use a variety of NAPI functions to do it. Luckily, the documentation for it is actually pretty good. I was actually kind of surprised at how good the documentation was in terms of the reference. So if you just go through this entire document to see what functions are available for working with stuff, and there's sections like working with JavaScript values. Here are the types and the functions you need to work with JavaScript values, and so forth. It's all in this one gigantic page. And that's the reference material that I use to figure out how to use these functions and which functions I need to use. For example, in order to get a JavaScript string into a form that you can work with in C++, you need to use one of these functions to sort of convert a JavaScript string into a string, a char array that you can work with in C. And if you have a number, you need to use this conversion function to convert it into a double or an int, a number format of your choice, etc. Now, if it's an array or an object, then what you need to do is use these here. Use a get property names function to get this would be like object.keys here in JavaScript. So nappy.getPropertyNames gets all the keys of the object, and then this stores it into this array that you've allocated over here. This nappy value stands for any possible JavaScript value. It could be a number, it could be an array, it could be in anything. And then you do the get the array length from the string, and then you loop through it, and then you get the element and so forth. You get the key. Oh, the element happens to be a key, and then you get the value. Is this the array one or the object one? This is the object one. So we got an element of the array, which ends up being the key that we want of the object. And then we turn that key into the string form so we can work with it in C++. And then we get the property, which I think this means access the property within this object with that key. And then we stringify the value, recursively calling this stringify value function, which knows how to deal with the variety of types in JavaScript. So anyway, so I did this. It took quite a bit of work and learning. And then after I done with this, I compared the performance, and this version was actually quite a bit slower than my JavaScript code, my JavaScript version of the stringify function. I had a couple of tries at trying to figure out why that was, but so far I have not been successful. I decided to switch my attention to the UI problem. But having said that, I do plan to come back to this problem and take a harder look at the performance of this thing, because it is actually important. Okay, so that was the thing number one, the performance of stringify. I haven't completed that to my satisfaction, but hopefully I'm going to come back to that and solve that problem. I have a couple of ideas of how I would approach it. On to the second thing, which is update the UI zoom debugger. So previously, let me show you a little bit of the UI that I have right now. Okay, so this is, for those of you who haven't seen this UI before, a better demo of it. I'm not going to do a full demo of this UI, but if you want to see it, you should go to github.com/airportyh/playlang. I have a bunch of videos about this deep zoom debugger UI. There's a 5-minute video as well as a 17-minute video where my colleague Huiqi and I have a little conversation about it. So basically I'm gonna zoom in here, and I'm able to zoom into the function calls that were called as a result of executing this program. And I just got, previously none of this, I broke this because I completely changed the data source. Previously the data source was coming from one file. That entire file was loaded into memory and then given to this debugger, and then this debugger would just go through the file and to grab the data that it needed in order to render this UI. I've changed that to, as I mentioned in the last status update, instead of logging the history in one giant JSON R file, now it logs to a SQLite database, which looks like this. It's got 4 tables now. Last time it had 3 tables, but I added one for the source code. So the source code itself is stored in the database. The reason I did that is so that in case after running this program you edited the source file, now that's going to be inconsistent with this program now, right? So by saving the source code in the database, that problem does not occur. Anyway, so I have a snapshot table which contains every snapshot of the state of the program at any point in the program. There's a bunch of objects which are stored in JSON R format, and there's for every function call that is made during the program, we also log a row in this function call table. So this database now drives this UI. And the way that is happening is I've written this Node.js/express server, which is actually, the code for it is very, very small. It's only 47 lines, which is responsible for handling queries for data within this database. So you can return function call objects based on a parent ID. Parent ID would be like the previous stack in the stack frame, where a function call is one frame in the stack frame. You can fetch a bunch of snapshots based on a function call ID. So every single snapshot of the program has a function call ID, namely the current function we're executing under. So given a function call ID, you can get a collection of snapshots, and then we can get objects in memory at any given time. So that's this object table. So given this REST-based API, this Zoom debugger actually fetches the data as it needs them, as it needs to render, and it only fetches the bits that it needs. For example, if it's only rendering this, then it actually doesn't need anything. Once we drill down, now it actually fetches the snapshots that the main function has executed within it, but not the details within the nested function calls yet. So it only had to fetch like line 2, 3, 4, 5, and 8, for example, as well as if there's a variable with a value there, like the answer was n, for example, it fetched that from the object table, and so forth. And if we drill down more, you can look at the requests here, by the way. Once it drills down, and then it's actually going to fetch a whole bunch of more data, one snapshot for every line that you see on the screen, but also for the pieces of the code that have boxes around it. That means that's a sub-function call, which can then be further drilled down into. And if you drill down into that one, and then it'll fetch even more information from the database to show you what's going on in that drill down. So that's what's going on. I just got this much working at this point, and it's actually very, very sluggish right now after the changes I made. So I'm definitely going to need to do some performance optimization on this UI. I can't tell you exactly what's the thing that's making it slow right now. And obviously one of the things that's obviously slow is the large number of requests that are being made to feed this UI. So one thing I could do is actually batch up the numerous requests into like batches, like say 10 at a time, or however many that came in within 100 milliseconds or something, and batch them all up into a single request instead of having multiple requests. And you can also see that not all, but some of the variable value display is already working now. The code is very, very gnarly right now, but I somehow got this to work. I'll show you just a little bit of the code here. Okay. So, first of all, to render the lines, we have something called the build child call map, which is basically given a let's say we're at the top level. We're going to build a map of the child function calls that exist within the body of this function. In this case, we only have one child function call. That's the play game function. So what this does is actually loops through every single line that was executed within this call of the main function, and see whether any line has a child function call. And this is going to find that it does. It actually does that by parsing the original source code and see if the source code has a function call expression on it. That's what this line does. And if it does, it's going to fetch the function call objects, these objects from the database. And the way it does that is by, let's see, so you can see these are all the function calls that were made. And the first function call is the call to the main function, right? And every one of these function calls has an ID. So this guy is ID 1. So if you fetch a function call, you can actually ask, hey, give me all the function calls whose parent ID is 1. And that means the parent ID is the previous function call, your parent function call. So if I find all the function calls whose parent ID is 1, that tells me the sub-function calls that occurred within the body of function call 1, which was main. So that just gives us this function call, which was a call to the function play game, and so forth. And this guy has an ID of 2. So if I ask, hey, within the function play game, what are the function calls that were made within it? I can call this API again, but with parent ID 2. This time we actually see a whole bunch of function calls because there was a loop. And that's what happens if we drill into the play game function. And so you can see all of these boxes. All of them are function calls, and then you can drill into them even more. So let's say I drill into one of these function calls. This is again sluggish. I'm going to need to improve the performance here at some point, probably very soon, because I get very impatient at sluggish performance. Like, I cannot work like this. Okay, there we go. Finally. So finally, like we drill into this is winner function, and then the variable value display on the side that's happening is also happening in a lazy manner, as in as it's needing to display it, it'll actually fetch it from the REST API and therefore from the database. And that code is very, very gnarly right now. Yeah, I'll talk a little bit about it, but it's so bad that I kind of, let me show you my 2 caches. Probably, I actually don't want to dig too deep into it, so I'm just going to talk about my 2 caches, and then that'll be the end of this, because I don't want to make this video too long. Okay, so I have 2 separate caches, the function call cache and the object cache. They actually look mostly alike. I just made one of them, made a copy, and tweaked the other one. This is a cache to store the function calls. The function call objects that are returning from the database, and then the object cache is to do the same thing for the object table. Basically, you use this get method to get either the object or the function call. And if it's already in the cache, it'll return it to you, but if it's not, it'll actually just return null. But it'll initiate the fetching for that object. So this time you'll get null, but when the data comes from the database, then the next time you call it, you'll actually get that object. The way this is set up to work is whenever one of these caches has completed fetching some data, it will actually notify the renderer via this onDataFetched function. And so basically whenever a fetch has completed, it'll notify the renderer. The renderer will re-render the canvas again. So then even though the first time you were needing that information, you just ignored it because you got a null value back. When the data comes, it calls the same code to render it, and the next time you get that object, it's actually there, and now you can render it. So that's what happened with these values. That's also what happened with the fetching of the child function calls. Yeah, so that's all I'll say about that. Do more of these status updates. Thanks for watching, and I'll see you soon.